So we have an action like this, and now in order to understand this space better, we consider the following. I want to kind of give you some sort of visualization of this one. First of all, we consider the space of all vector space norms on the two-dimensional standard vector space, which means that, so this is meant to be a vector space norm, so it is 0 if and only if the vector is 0. Everything is sort of non-homogeneous, so this is actually then automatic. If it's so we want some form of triangle inequality, which we can then also put the so-called strong triangle inequality, and it's compatible with scalar multiplication in the sense that if I multiply it with a scalar lambda in L, then this is the P-adic absolute value of lambda times the norm of V. So it's just the set of all vector space norms on this P-adic vector space, on this standard vector space, modulo. Well, we consider two such norms equivalent if they are scalar multiples of another. So we say that a given norm is equivalent to a scalar multiple of itself for any positive real number R. So, these are sometimes called the space of homothetic classes. Homothetic classes of norms on this two-dimensional standard vector space, and it naturally it carries a compact open topology, and so we can ask, what is this as a topological space? There's a very nice answer for this. Goes back to Goldman and Ivahori. It's not really very hard to see this, at least for GL2. One can do everything in higher dimensions. Here, but Goldman and Ivahori, that T is naturally homeomorphic to a P+1 regular tree. P+1 regular tree, by which I mean the following. So we have vertices, and for each vertex there are P+1 edges connected to this vertex, and so on. So this is the picture when P is 2. It looks like this. Where really so any edge is homeomorphic to the standard closed unit interval between 0 and 1, and they are sort of put together according to this, to this scheme here. So it's like this. It's an infinite P+1 regular tree. At any vertex, there are P+1 edges coming together. And and then we have a nice map. This is also sometimes called the Buertitz tree of the group GL2 or SL2. And then we have a G, and there's natural action on this space. If you have such a norm, an action by our group G, you have a norm, you can you get a translated norm by any group element will give you a new norm, and so there's also a nice action of our group on this tree, which permutes transitively the vertices. And there's a G equivariant map. I call it a retraction map R from this P-adic upper half plane to this tree, and it's defined as follows. A number in CP, but not in L, gives rise to a norm, or rather to a homothetic class of norms, where this norm is defined on a vector like this as the complex, the P-adic absolute value of AZ plus B. And this is the unique extension of the P-adic absolute value to this field ZP, and this is never going to be 0 except if AB is the 0 vector, if both A and B are 0. Otherwise, this can never be 0 because Z is not in L. Okay, so we get a norm after this, and let's see what a pre-image of a vertex looks like. Pre-image, I should say there's a kind of distinguished norm, in a certain sense, the distinguished norm V0, which corresponds to the norm, so V0 corresponds to the norm, which sends a vector to just the maximum of the coordinates. This is certainly such a P-adic vector space norm, and we have this one. So now, what is sort of the pre-image of the vertex V0? This is the set of all elements in CP that are of P-adic absolute value less or equal to 1, but which have also the property that the distance between any so-called P-adic integer, or equivalently between any number, the distance to any number 0, 1, 2, 3, and so on up to P minus 1 is equal to 1. Sorry, the condition is this. For all A from 0 to P minus 1. How can we think about this? Well, it's kind of, I'm only drawing a picture when P is 2. So this is sort of the disk where the absolute value of Z is less or equal to 1. This disk in CP. And then this condition here means that Z is not of distance less than 1 to 0, 1, 2, and so on. So we have two such so-called residue disks in this case, or P minus 1, P residue disks in general. Here we have where the absolute value of C, the P-adic absolute value of C is strictly less than 1, and here where the P-adic absolute value of Z minus 1 is strictly less than 1. And so this set consists of these disks, where these two disks are removed. So yeah, maybe. So these are removed. So we can think of this as sort of, if you want, a sphere with three. The disk in which we remove two disks is sort of the same thing as a sphere in which we remove three disks. Think of this sort of as the outer. If you have a sphere and you remove one disk, what remains is topologically the same as a disk. And then we can also draw, can sort of deform it a little bit, and so it's kind of pair of pans. And the same works for every prime number P, of course, in which we have then here a sphere with P plus 1 disks removed. And we have here some such space which sort of has p plus 1 ends. Now, what is the pre-image of, and the same is true in a sense, I mean, the same is true that in the topological structure, the structure of the pre-image of any vertex looks like this. Now, the pre-image of any edge, on the other hand, is always an angulus, like this. Like, for instance, the set of Z in CP with the property that P minus 1 is strictly less than Z is strictly less than 1. This would be one might also call it an open angulus. Then how do those structures fit together to give the whole P-adic upper half plane? So now taking the pre-image of this one under this retraction map, the pre-image of this one, and connect them via the pre-image of the edge. So when I say edge, I mean open edge, without the vertices at the end. The open edge. Well, this then looks as follows. So maybe let's start here with an edge, and here with those vertices. So the pre-image of this vertex looks like this sort of pair of pans space. Then we have the pre-image of this open edge, which is an annulus like this, right? I mean, this kind of annulus is sort of looks also a little bit like a cylinder, stretch. And then we have another pair of pans here, and then we have another cylinder. This is the whole, this small cylinder is the whole pre-image of this open disk. Then we have another pair of pans here, and then we have another cylinder, and so on. So the upshot is that we should think of this P-adic upper half plane as being
lots
like
of pans.
Yeah.
And lots of
Yeah. Now I should stop somewhere. So the upshot is that it's like a tube around the tree, and that's really a very good, very good way to think about it. The analogy, I mean, with the complex upper, the complex upper half plane, or with P1C, is also in some sense nice, because if we have here P1C, this is the Riemann sphere, and here we have P1R, this is the equator. It's like S1, and the complement is the upper and the lower half plane. Okay, so it's not quite only the upper half plane, but this is related to the fact that we are here looking at GL2. We would be looking at GL2R, which does not act only on the upper half plane, it acts on the upper and lower half plane. And in the P-adic world, well, we can also morally think of P1CP as sort of like a Riemann sphere. And what would you, and now we are taking the complement of P1L, let's say P1QP, to think about something concrete. But this space, however, I mean, there are zillions of points here. And when I remove all those points, I get an infinitely punctured sphere. This looks pretty terrible. However, I can think about it as a tube around this tree. Namely, the points that are missing correspond to the ways I can move towards infinity. I can move sort of out of the tree. Or in other words, the points that I'm here missing, that I'm removing, correspond to the half lines in the tree.
So it's uncountable set, right?
Right. Exactly. And every such sort of path towards infinity, every such path corresponds to one and only one element in QP, except there's one path which sort of goes to infinity. And then we have sort of this picture. Okay, so I think we started a little late, right? That's it here. And now I'm going to introduce this covering space. Okay. Okay, so I mean, where did we get this covering space from? Nice. So the fundamental theorem about this P-adic upper half plane is that there exists a family of formal groups over it. Of formal groups in two variables. So f, z is a parameter on the P-adic upper half plane. So it's sort of a family in two variables, meaning so a two-dimensional of two-dimensional formal groups. It means it is each such formal group is given by a pair of power series fz1 in those four variables and fz2 in those four variables. And so morally what you do is you take a pair of points s and st and another pair of points s prime t prime, and then you plug them into those power series and you get another pair. So this is like the group law. But it's only a formal group law. These do not really have to converge somewhere, at least not a priori. But still one can make sort of sense of this. So there's a so z, the parameter z is in this P-adic upper half plane. And we can think about it like this. So here's our space sigma 0, and here, so symbolically, I'd like to think of any of such formal groups laws. You may think of it as something like an infinitesimal neighborhood of the origin in a two-dimensional vector space. And so for each point z in here, there's such a formal group law in two variables. And then we can consider the torsion points. So the whole family, I may call it F, and in a certain sense, the whole family itself constitutes a space over the P-adic upper half plane. And then we can consider the P torsion points. The P torsion points. This is sort of some subspace in here. F P torsion points. So meaning in each fiber, in each formal group, a subgroup of points which are annihilated by multiplication by P. So this is then the P total. And we remove, however, we remove the zero section. any such. There's some distinguished section here, which is the zero section. And that gives a space, so it consists sort of those layers here, but not the zero section. We remove the zero section. And this gives a finite map, a finite surjective map of degree. Well, each of those p-torsion groups has exactly p-square elements. And so if we remove the zero section, we get a map of degree p squared minus 1. Moreover, each of those formal groups is equipped with an action of some division algebra. Maybe so I now have to be sort of very quick. There's a natural covering group on here. So this is a covering with this group of deck transformations which is isomorphic, this covering group, to the multiplicative group of the field with p-square elements. This group has p-square minus 1 elements. So this is exactly why the degree is p-square minus 1. This is the covering group. So it's a nice finite covering. And how does it look like? Well, looks like as follows. So I call the covering map F. So what is the pre-image of such a pair of pairs? Let me just write here any vertex. We consider a vertex, and then here we have this kind of pair of pairs thing. This is the pre-image in sigma naught. And this one, it kind of looks a little bit similar. It looks like a Riemann surface with p+1 disks removed. However, it is of a higher genus. It's kind of like a Riemann surface of higher genus. In fact, it's like a genus, a curve, like a Riemann surface, a curve of genus. We can actually compute this explicitly. P times p minus 1 over 2 with p+1 disks removed. The p+1 disks are sort of the ends of any such space, are the same and correspond one-to-one to the ends that we have here, with p+1 disks removed. And the pre-image of what we had over an open edge, here the open edge, the pre-image in sigma naught of the open edge is an annulus, and the same is true here. That's also an annulus, but this map is, as before, it's a p+1 to 1 map. It's a covering of an annulus by an annulus of degree p+1. So all those spaces then fit together. We try to sort of, here we have and so on. So over any such pair of pairs, there is a higher dimensional. In fact, if the number of disks is 3, then p is 2, and when p is 2, the curve has genus 1. So there shouldn't be 3 holes in here, there should be just 1 hole in here. So this space is mapped to here, then I should have drawn this a little bit more symmetrical. So this is going here. This is here. This is here, and so on. And if we have sort of another pair of pants here, then the space that lies over it under this covering map is again something, a curve of higher genus. So this is mapped to here. Now we are interested in the space of functions of analytic functions on this covering space. And analytic functions not just in the sense as we defined it before, locally analytic functions, but there's a stronger sense of there's a stronger notion of rigid analytic functions. John Tate has sort of made the impossible possible by introducing this concept of rigid analytic functions and the concept of a rigid analytic space, which makes it possible to talk about analytic continuation over a totally disconnected space. All these spaces, as I define them, with sort of the most natural topologies that you can see around, are totally disconnected. Because also this field, with its natural norm topology, valuation topology, is totally disconnected. However, there's a way to put a stronger topology on here and to make a notion of analytic functions which is much better. And we are interested in these other functions. So we'd like to understand now the space of so-called rigid analytic functions. For this, we need to sort of do something which is called specialization, or one way to understand this space is by sort of introducing locally coordinates on the space, but in a sort of coherent way, such that we can represent these subspaces by numbers in CP that we can reduce modulo P. So how does that happen? So specialization to characteristic P is sort of, so for sigma naught, this works as follows. For sigma naught, this is like this. So again, we have this set of numbers z and cp that are of absolute value less or equal to 1, but that also have distance 1 to any number between 0 and p minus 1. And if we take such a number and reduce it not only modulo p, but modulo the maximal modulo the following ideal, so we get a number which lies in the algebraic closure of fp. So we take a number z in here and send to z modulo the ideal m, which is an ideal in the so-called valuation ring of cp. So it consists of just of all numbers w of p-adic absolute value less than 1. But because we have this condition here, we do not get all elements in fp bar, except those elements which are actually in fp. And I like to think of this again as sort of like a characteristic p upper half plane, like something like p1 fp minus p1 fp bar minus p1 fp. So there's sort of also a characteristic p analog of those spaces. And we may think of this as like, a little bit like a circle where we have removed the rational points, the fp rational points. Say if p is 2, 0, 1, and infinity. And then we glue all all those P1s, so as an algebraic variety, we glue them all together. We have here P1, and then we get a tree of P1s, and this tree of P1s, any two P1s intersect in exactly one point transversally. These are meant to sort of be in transversal intersections here. And what we have here is sort of, again, it's like a pair of pans subspace. This is mapped to this open P1 where we have removed these three intersection points. Then we have an annulus here, and everything that's on this annulus is mapped to this single point here, to this intersection point. Then we have another pair of pans here, which is mapped to this open P1, and so on. So this annulus is then mapped to this intersection point, etc., etc. So this is now going to be an algebraic variety with infinitely many irreducible components. And we can do the same for the covering space. Let me just sort of indicate this because it has a nice structure. So if we do here specialization, so F inverse of, so you remember this is sort of this curve of higher genus that we considered before. Where does it specialize to? Well, it specializes to a curve, to an algebraic curve inside P2 in characteristic P with the property, with the equation defined by the equation x y to the P minus x to the Py is equal to z to the power P plus 1. So this defines a so-called plane algebraic curve of the same genus as we had before, this formula P times P minus 1 over 2. And so I like to sort of draw it as a little bit more complicated curve, not just a circle. And the specialization map in this case goes from this covering space onto a tree of curves. They are all isomorphic of curves of type C. Of curves all isomorphic to C. Again, sort of we have one such curve C, and then we have another one which intersects this curve transversally, and another one, and yet another one for each. There are sort of P plus 1 distinguished points, and then here we have such a curve of higher genus, and here we have such a curve of higher genus, and here we have, and so on. So kind of the combinatorial structure of how those curves intersect is exactly the same as we had it before. And any of those curves lies over a P1 by sending a homogeneous, a point given by homogeneous coordinates x, y, and z to x and y. X and y can never be simultaneously 0 if they lie on this curve, because if x and y are 0, then z is 0. And so it's not a point in P2. So this gives a covering map, and that map is actually étale. So it's unramified except at those intersection points. And maybe so I think I've now basically explained all those structures, these geometric features. So at this point there's some ramification going on, but apart from those points, so the map in characteristic P, so there is, maybe I'll finish with the following diagram. which suffices then sort of to say that, so we have here those spaces in characteristic 0 on the covering map. It's a very nice unramified covering map. We have here a specialization map to this tree of curves of type C. We have here a specialization map to a tree of P1s. And we have sort of the so-called reduction of this map, modulo P, sometimes called modulo P, which is a map from here to here, and which is also almost like, a very nice covering map. It's ramified at those points here, but otherwise it's a very good sort of it's a so-called étale or generically étale map. In fact, one can be more precise. So, unramified outside the intersection points, and because of this, you can say sort of so these structures so the main theorem is that if we now consider the space of all those rigid analytic functions on the covering, again this has an action by our group GL2L, and that itself is not a locally analytic representation, but we can take the continuous dual. So this dash means continuous dual. And this is now a locally analytic representation. And this representation is so-called admissible locally analytic representation. That means it satisfies certain finiteness properties. These finiteness properties have to do with the structure of, again, the continuous dual of this space after taking the dual is the space itself, so the double dual. And admissibility means, in a sense, that this is a nice module. It's a nice module over some completion of the group ring. A certain P-adic completion of the group ring, which I'm not going to introduce here. So this would be a little before. And the reason why this is the case can be seen by making sort of use of those structures in characteristic P. In fact, so what we do is we sort of these spaces here, these schemes, these algebraic varieties live in characteristic P, but we can consider sheaves of functions in characteristic 0 on it. And then one can make use of various results that people have developed in the context of what's called rigid cohomology, or crystalline cohomology, or rigid cohomology, and they have proved certain finiteness theorems for instance, the push forward of a sheaf on here to a sheaf on here. And this then can be used to show that this space has some finiteness property over this completed group ring. Okay. Thank you very much.